Hello and welcome to the Operator's Best Practices for Hot Water Systems in Commercial Food Service Facilities.
There will be a speaker icon on every slide which will start playing the voiceover.
The information found in this presentation is a distillation of lessons learned from multiple laboratory, field, and industry characterization studies performed for the commercial food service industry. These lessons have been compiled into a new operator's guide for advanced water heating within the food service industry by a team of energy industry professionals from TRC and Frontier Energy. This document is accessible at the link on this slide and goes into further detail than this presentation. This was made possible with funds from the CalNext program.
This 2023 design guide builds from previous iterations. The first design guide was published in 2010 and was funded by PG&E and the California Energy Commission. The second revision of this design guide was first published in 2021 with funds from SoCalGas.
By the end of this presentation, viewers should be able to describe the water and energy savings associated with proper system performance, understand when to replace equipment, and understand how to design an effective staff training program.
This presentation and the design guide can both be found at the CaliforniaEnergyWise.com website. This website also has multiple other resources for food service and energy industry professionals. The California EnergyWise website includes directions for energy surveys to help food service operators understand their energy usage, design guides to help facility designers design more energy efficient kitchens, links to upcoming in-person and virtual seminars, as well as recordings from previous seminars, which contain tips on best operating and design practices, as well as results from lab and field studies, instructions on how to participate in Frontier Energy's Try Before You Buy program, which allows food service operators to test drive new cooking equipment, calculators to help compare the energy and cost impacts of different pieces of kitchen equipment, and information about how to access rebates for food service equipment. Section 0, Preamble. Why do we care about hot water systems? Hot water is critically important for commercial food service facilities because it provides most of the sanitation. Hot water is largely the lifeblood of restaurants. Without it, operators cannot clean their hands, wash dishes and equipment, or cook food. Hot water touches virtually every part of a commercial food service facility. Health department regulations basically say that you can't run a restaurant without adequate hot water delivery, basically for fear of getting people sick. Hot water systems are also highly energy intensive. In California, they use 340 megatherms per year, which accounts for about 16% of all commercial gas usage statewide. Hot water systems can also account for as much as half of a commercial food service facility's energy usage. So it's very important for a facility's bottom line as well as for its overall operation. The utility rates used to calculate values in this presentation are in the table to the right of this slide. The water and wastewater cost is $14.16 per 100 cubic feet. The gas rate is $1.65 per therm, and the electricity rate is 33 cents a kilowatt hour. These rates reflect current California utility rates and projections for 2024. Generally speaking, utility rates are rising and are rising a bit faster than inflation. And they're projected to continue rising a little bit faster than inflation throughout the rest of the decade. Electricity and gas rates have been going up as a general trend over the last 10 to 15 years. And electricity is set to actually outpace gas in terms of how much it's going to increase. This is going to make fuel switching from gas to electricity a little bit more difficult financially going forward. But later in this presentation we'll show that it still can be cost effective in some cases.
These tables compare the cost impacts of water and energy efficiency and operating patterns. The first table compares Restaurant A to Restaurant B. Restaurant A is a generally efficient hot water system, and Restaurant B has a generally inefficient hot water system. Restaurant A's dish machine is only 3 years old, whereas Restaurant B's dish machine is more than 5 years old and has some serious operating problems. They both serve around 500 meals per day, but Restaurant B uses almost double the hot water that Restaurant A uses because it's using substantially less efficient fixtures. Similarly, Restaurant B uses 1.5 times as much gas as Restaurant A does. Restaurant A uses less electricity than Restaurant B, and all of this adds up so that Restaurant A is only paying 17 cents per meal for its hot water usage, whereas Restaurant B is paying 25 cents per meal for its hot water usage. The second table compares the same restaurant doing a dinner service on Wednesday and a dinner service on Thursday. It compares the impact of operating patterns on the cost per meal. On Wednesday dinner and Thursday dinner, this restaurant served roughly the same number of meals. However, during Wednesday dinner, the staff wasn't using the equipment as designed and used more than double the amount of water, almost triple the amount of hot water that the staff used for Thursday's dinner service. That led to the cost per meal for Wednesday being 24 cents per meal, whereas on Thursday it was only 15 cents per meal. The only thing that changed between these two lines on this table was just the staff and how well trained they were. This is the operator's path for savings. Step 1 is to commission new equipment and systems properly, because if it isn't installed correctly, it will never work correctly. Step 2 is to operate systems efficiently and train staff on how to use each piece of equipment as designed. Step 3 is to maintain systems and specify preventative maintenance. This means creating a maintenance schedule to ensure that each piece of equipment is operating as the manufacturer intended it to. Step 4 is to specify efficient equipment for replacing on burnout and to create an equipment replacement schedule. Section 1. Commissioning. Properly commissioning the dish machine is probably the most important step an operator can take to ensure that their hot water system stays efficient for as long as possible. Upon installation, the commissioner should check the tank temperature, the rinse temperature, the inlet hot and cold water temperatures, the exhaust flow rate if there is an exhaust hood in the dish room, the rinse pressure, the input hot water pressure, the input voltage and amperage, the rinse water consumption, and the chemical consumption. The commissioner should also perform a catch and weigh test to ensure all of the water usage is as the manufacturer intended it. If any of these metrics are off, the manufacturer should be contacted and there should be some kind of maintenance performed on the machine. It can also lead to a situation where a machine needs to be replaced. Tank temperatures can range from 120 to 150 degrees Fahrenheit and need to be checked to ensure the proper functioning of the tank's drain system and temperature control. The rinse temperature of high-temperature rinse machines should be 180 degrees, and the rinse temperature of low-temperature rinse machines should be about 140 degrees depending on the chemical supplier. This is important for high-temperature machines because the 180-degree water is needed for sanitation. For low-temperature dish machines, the temperature is needed to activate the sanitizing aid chemical. The inlet hot temperature needs to be checked for high-temperature machines to ensure that the booster heater only has to work to its allowable limits and to ensure that the rinse temperature is always met. The inlet hot water temperature is the same as the rinse temperature for low-temperature rinse dish machines. The inlet cold water temperature needs to be checked for heat recovery dish machines because the ventless function of heat recovery machines can sometimes be compromised by inlet cold water temperatures over about 80 degrees. The exhaust flow rate needs to be matched to the exhaust fan speed for adequate ventilation of the dish room, and the rest of the bulleted items in this list need to be checked for proper commissioning of the dish machine. The catch and weigh test is a useful method of determining the flow rate of fixtures and is an important part of commissioning a new hot water system or installing new fixtures. This test is performed by measuring the amount of time it takes to fill a 5-gallon bucket with a fixture. Example procedures for pre-rinse spray valves and dishwashers are included on this slide. Here are some best practices for commissioning a new hot water system. The operator should measure the delivery temperature at all fixtures with a handheld temperature sensor. The wait time for hot water delivery should be measured at lavatory hand sinks. Health department officials will sometimes perform this test during a sanitation inspection, so it is a best practice here. Determining the wait times at any remote fixture is especially important because they tend to have the biggest hot water delivery failures. Operators should use the catch and weigh test to check the operating flow rates at all fixtures. The flow rate should match the manufacturer's specifications. If a fixture does not match a manufacturer's specifications, a technician should be contacted immediately. Finally, the two biggest flow rate fixtures, which are often a compartment sink and a mop sink, should be operated simultaneously to ensure they don't starve the hot water system of hot water. If the flow rate is throttled when both fixtures are on, there may be a problem with the water heater and a technician should be contacted. When commissioning a hot water system, it is particularly important to know the water quality at your facility, as hard water can lead to a whole host of problems for many pieces of equipment. At the water heater, it can lead to cracked heating elements and flame diverters. At the dish machine, it can cause cracked elements and plugs in the exhaust system. This is especially problematic for heat recovery dish machines as their heat exchangers can foul, which can prevent the machine from meeting its final rinse temperature. Major pieces of equipment should have allowable hardness limits on their specifications sheets. If the hardness in your area is higher than the limits for the dish machine and water heater, it may be necessary to install a water softening system or a reverse osmosis system. Section 2. Operation. Dishroom staff should be trained on the proper operation of all dishroom equipment and should be encouraged to point out equipment that has any change in its operating pattern. Staff can be the first line of defense for saving hot water and for replacing damaged equipment. In this video, a staff member is using a floor cleaning hose and a scrapper to pre-rinse a sheet pan before loading it into a dish machine. Between the scrapper and the floor cleaning hose, there is over 5 gallons per minute of water usage, even though there is a pre-rinse spray valve rated at less than a gallon per minute installed at this workstation. Additionally, the dish machine is overspraying into the scrapper sink, indicating a maintenance problem that this staff member should report to management. Pre-rinsing is the practice of removing food debris so that the dishwasher only has to sanitize the dishes. It is a critical step for the functioning operation of any dish room. A pre-rinse sink is used in most dish rooms. Pre-rinse spray valves are the most common piece of sanitation equipment found in most facilities. It is used to rinse stuck-on food debris from wares. Pre-rinse sprayers are intended to be used on wares after they have already been dry scrapped, where staff has manually removed as much of the food debris as possible, either by hand or with a scraping tool. Dry scrapping is the most important water-saving training measure for a facility. It is recommended that facilities have a dedicated dry scrapping station with a compost collecting bin and any scrapping tools located near where dishes enter the dish room. Other pieces of equipment used for pre-rinsing include food waste collectors, disposers, and scrapping troughs. Restaurants typically have pre-rinse sprayers as their only form of pre-rinsing, but cafeterias can have some heavier-duty equipment. Scrap collectors use 1 to 2 gallons per minute of fresh water to create an 8 to 30 gallon per minute recirculated waterfall. These can and should be on timers to limit their water usage. Disposers usually use between 3 and 10 gallons per minute of fresh water. They are essentially upgraded versions of the under-sink garbage disposers installed at many residential kitchen sinks, but they have a dedicated water inlet instead of depending on the sink's water to clear chopped up food from the blades. Troughs are essentially a river of tepid water running through the dish room. Staff dunks dishwares in the trough to scrap them. They typically use between 2 and 3 GPM of fresh water. The next few slides will cover data from a pre-rinse operations field study where about 20 cafeteria dish rooms were monitored for their water usage. This study can be found in the references section of the operator's guide with the title PRO Operations Field Comparison. Dish rooms can sometimes be intense places to work. Wares must get clean quickly to ensure the proper operation of other parts of the restaurant. Staff on the cook line can't cook without clean implements, and patrons can't eat from dirty plates. Sometimes, when equipment malfunctions, the dish room staff need to get creative, which can lead to misuse of equipment. At one cafeteria monitored for this field study, engineers found that staff resorted to using industrial floor cleaning hoses for want of a properly functioning trough, disposer, and pre-rinse sprayer. Each hose had a flow rate between 5 and 7 GPM and used almost 1,300 gallons of water per day for pre-rinsing alone. Had the equipment been properly installed and functioning, the pre-rinse water usage would have been about 300 gallons per day, meaning the poorly trained staff and faulty equipment caused about 1,000 gallons of water waste daily. The example from the last slide was not the worst performing site in this study, and was far from the only example where equipment was misused and proper procedures were not followed. This table shows the average water usage from the pre-rinse method at each site. The most efficient method for pre-rinse operations was dry scrapping, but a scrapper installed with a pre-rinse spray valve was also very efficient. The main takeaways from this study were that operating practices can have a huge impact on dish room and water and energy usage, and that dry scrapping can save a lot of water. The most water waste from this study came from sites where equipment was misused. The other main takeaway from this study was that training staff on the proper operation of dish room equipment and incentivizing staff to report malfunctioning equipment can prevent this waste. The data shown on this slide comes from a field study where the pre-rinse equipment at a large cafeteria was monitored for its water usage. The top graph shows how often the average daily pre-rinse water use per meal reached certain thresholds. On June 3rd, it averaged 0.7 gallons per meal. On June 4th, the facility averaged 3.6 gallons per meal. The cafeteria did not have any change in its equipment, so the only real change that could have affected the water consumption was the staff's operating pattern. The bottom graph shows the average use per meal period. For breakfast on June 3rd, water use averaged 1.0 gallon per meal. Lunch averaged 0.8 gallons per meal, and dinner averaged 0.3 gallons per meal. In contrast, breakfast on June 4th averaged 4.2 gallons per meal, lunch averaged 1.1 gallons per meal, and dinner averaged 5.9 gallons per meal. Between dinner on June 3rd and dinner on June 4th, water use increased by a factor of 20. Staff during the dinner period on the 3rd focused much more on dry scrapping and only sparsely used a pre-rinse spray valve to provide pre-rinsing, whereas staff during the dinner period on the 4th misused floor cleaning equipment and disabled the recirculating function of the scrapper and trough. A proper training program includes standard startup and shutdown procedures for all equipment, standard operating procedures for all equipment, designation of a clean and dirty zone in the dish room, daily cleaning schedules and procedures for all equipment, close of shift and facility shutdown procedures, and an incentive to report malfunctioning equipment to management. The next few slides include sample checklists for startup and shutdown of a hot water system in a commercial food service facility. A copy of this checklist is included as a PDF at the end of this presentation. Finally, a monthly maintenance checklist should be followed by management once per month. This should include places where performance data from major equipment can be recorded and yes/no questions to remind the viewer to check everything on the list. In addition to the items on the sample list provided here and as a PDF at the end of this presentation is to perform a water softener or water quality check. The water quality entering the hot water system should be checked to ensure that it is below the allowable limits for the water heater and dish machine. Section 3. Maintenance. There are 6 main steps to keeping hot water systems maintained. Step 1 is to listen to staff. Especially if they've been incentivized to report operating problems to management, they should be able to help to quickly identify equipment that needs to be fixed or replaced. They're the people who are actually handling the equipment, so they'll be the quickest to identify problems. Step 2 is to check utility metering data. This data can be especially useful if the water utility provides any smart metering where day-to-day or hour-by-hour data can be easily accessed, but even keeping a record of water use over time can be helpful in identifying bigger problems. If this month's water usage was higher than last month's and there wasn't a significant uptick in the number of meals served, this can be a cause for concern and further investigation. Step 3 is to identify and immediately address leaks in any fixtures and the hot water piping. The table below shows the water cost per year of various kinds of leaks. Part of the startup and shutdown procedures should be to check for leaks. Step 4 is to identify burnt-out pre-rinse equipment. Making sure pre-rinse spray valves are operating adequately and making sure scrappers and troughs are recirculating properly are important steps for preventing hot water waste. Any automatic shutoff devices, such as occupancy sensors installed on any equipment, should also be checked periodically. When burnt-out equipment is identified, the operator should have that piece of equipment replaced as soon as possible. Step 5 is to identify when dishwashers need maintenance. It can sometimes be difficult to identify operating problems with dishwashers, but common visible problems are overspray, where water sprays from the washing compartment onto the dish loading tables, leaks, and worn-out curtains on conveyor machines. It is also important to check the flow rate of the dishwasher periodically with the bucket catch test. Step 6 is to follow a maintenance and replacement schedule. Sample maintenance and replacement schedules are provided in the next slides. This is a sample maintenance schedule. The information that should be included on maintenance schedules is a list of each fixture and its make and model information, the contact information for the service technician, a list of maintenance checks to be performed by the operator, and the tune-up time period. It is also important to keep a maintenance log for each piece of equipment, which should include the date of the last service and what repairs were performed, as well as the original date of installation. This is a sample replacement schedule. The most important information on this chart is the installation date, the date of expected burnout, and the date to specify and order a new machine. Dish machines have expected lifespans of about 7 years. Pre-rinse sprayers have expected lifespans around a year, and most other fixtures have expected lifespans between 4 and 6 years. It is generally a good practice to specify a new machine about 6 months before the expected burnout date. Section 4. Retrofitting and replacing. Pre-rinse sprayers are the easiest fixture to replace, both in terms of the ease of installation of a new sprayer and the cost of the sprayer itself. Pre-rinse spray nozzles are usually available for less than $100 and can usually be swapped out by an operator without the need for a service technician. Because common pre-rinse sprayers have flow rates around 1.2 gallons per minute and efficient pre-rinse sprayers have flow rates around 0.7 gallons per minute, these fixtures also offer significant water and energy savings upon replacement. Some design and operating best practices are to install multiple pre-rinse spray valves in larger facilities, as this allows more staff to pre-rinse dishware during busy periods, to replace pre-rinse spray valves frequently to ensure an efficient dishroom operation, and to train staff to dry scrap as much as possible, as this will further reduce water and energy usage. If staff is trained poorly and encounter scaled over or otherwise poorly performing pre-rinse sprayers, they may use floor hoses instead of pre-rinse sprayers or attempt to drill out the scaled over nozzle. Floor hoses have typical flow rates around 10 gallons per minute, and drilling out the scaled over nozzle can increase the sprayer's flow rate to as high as 5 gallons per minute. Replacement is cheap and easy and is overall a much better option than misusing equipment. Operators who have recirculation systems should consider installing recirculation controllers. They can save up to 95% of the gas used to operate the recirculation system and also allow storage water heaters to operate at a higher efficiency, thus saving energy. There are smart plug style controllers that are particularly easy to install. Operators should specify exhaust heat recovery dish machines on burnout. The table below shows results from a field study where a conventional high-temperature door-type dish machine was replaced with an Energy Star machine, then a heat recovery machine. The heat recovery machine outperformed the conventional and Energy Star machines, saving the operator about $3,200 per year in the process. When specifying a retrofit dish machine, the operator needs to consider the new machine's footprint and the loading and unloading table layout. The operator should check on the retrofit machine specifications sheet to ensure that the new machine is compatible with the previous setup. If this is not done, tables may need to be replaced, which can dramatically increase the cost of installing the replacement machine. The operator should also check the water pressure and electrical capacity in the dish room to make sure that the new machine is compatible with the current setup. A common problem when switching from a low temperature rinse dish machine to a high temperature rinse dish machine is that there is not enough power in the dish room to operate the new machine, which requires an electrician to run new electrical line from the main breaker and sometimes to install a subpanel. The first step in selecting a water heater for a commercial food service facility, once the rest of the system is designed, is to select the kind of water heater that is desired. The most common water heater type is the standard efficiency natural gas fed storage water heater. The pros of this are that these heaters are very simple, they're robust, they're low cost, they're easy to specify, easy to fix, easy to replace, and relatively cheap with an upfront cost of between $2,000 and $9,000 depending on the size of the heater and how much storage it has. The cons are that it only has an 80% thermal efficiency, they can have significant standby losses, they can run out of hot water, especially if they're undersized, and they have a short lifespan in commercial kitchen environments around 5 years. Condensing water heaters are more efficient than standard storage water heaters. They work by running extra lengths of exhaust through the water tank. This cools the exhaust and allows the water in the combustion exhaust to condense, which provides more heat to the water in the tank. The pros are that these heaters boast a 95% efficiency, they can have a much smaller standby loss because they're usually insulated, there's potentially a lower cost of install because sometimes these heaters can be installed with a PVC exhaust instead of standard ducting, and these pair very well with master mixing valves and demand recirculation controllers because their condensing function requires tank stratification to work. The cons are that these are more complex, which means that they're harder to work on. When installing these water heaters, you have to manage the condensate. The condensate produced by these water heaters is usually fairly acidic, and so there needs to be some kind of buffer installed on the condensate drain or a condensate drain installed in the floor to handle that. These are not the standard, and so less plumbers can work on these. They have a higher first cost, so when they run out of water, they cost more to replace. And like other water heaters, they have a relatively short lifespan in certain commercial kitchen environments, especially ones where they run out of water often. Tankless water heaters have become much more popular in smaller commercial food service facilities over the course of the last 10 to 15 years. They're sought after because of their smaller footprint and because outside installations are possible, which frees up space in the facility. These units also boast that they don't have a standby loss because they don't store hot water. The cons are that they have a significant pressure drop. These water heaters have a control system which allows them to limit the outlet flow of hot water so that they can meet their temperature set point. If multiple large points of use are run at the same time, these units will starve the entire hot water system, which can lead to critical hot water failures. There are minimum water flow limits on these as well, so if the demand is small enough, they will just send cold water in the hot water outlet pipe. To reach a facility's demand, the facility probably will need several units. These tankless heaters also have much higher gas input rates, which leads to higher installation costs by running larger diameter gas piping. Increased maintenance is required for these heaters in commercial food service facilities. Electric resistance water heaters are not very common in the commercial food service industry. The pros of these units are that they are zero net carbon and decarbonization friendly because they only use electricity. They are also simple and easy to work on. The cons are that they have a large amperage draw, which would require a relatively large service panel for commercial kitchen-sized loads. This would also lead to significant energy use with a more expensive fuel. That means that these heaters are much more expensive to run than ones fed with natural gas of similar size. Finally, there isn't a huge thermal efficiency gain over gas water heaters. Gas storage water heaters have thermal efficiencies around 80%, and electric resistance storage water heaters have efficiencies around 90 to 95%. So the energy efficiency gain isn't enough to offset the big increase in fuel cost. If California continues to decarbonize, heat pump water heaters are likely to become the most common type of water heater in commercial food service facilities. Heat pump water heaters boast a coefficient of performance as opposed to a thermal efficiency. They siphon energy from the air and their surroundings to heat water. An electric heat pump water heater with a COP of 2.5 would produce 2.5 kilowatt hours of useful water heating for every kilowatt hour consumed at the wall. This would provide very large energy savings over conventional gas water heaters and could, in some cases, be enough to offset the higher fuel cost. Heat pump water heaters can be packaged or split, which refers to whether the evaporator is connected to the hot water tank or remote. If the evaporator is placed in a hot room in the facility, the heat pump can provide some free cooling as an added benefit. The cons are that these units require large volumes of hot water storage to compensate for their slower recovery, which means that they require a larger footprint. Heat pump water heaters also require ventilation and have about twice the upfront cost of traditional water heaters, so there are significant barriers to their widespread adoption in the commercial food service industry without some level of incentivization. The first step to running an efficient hot water system is making sure your system is commissioned properly. Staff should be trained in efficient use of hot water system equipment, especially the practice of dry scrapping, as much as possible. Daily startup and shutdown procedures save water and energy and also prevent mechanical failures of devices. Staff should be trained to be the first line of defense in reporting mechanical problems. Regular and frequent maintenance should be performed on all major fixtures. Equipment lifespans should be planned for, and replacements at end of life shouldn't be an emergency upon burnout.
Thank you for listening to this presentation. For more information on designing efficient hot water systems for the commercial food service industry, please refer to the design guide, which is accessible at the link at the top of this presentation. For information on operating an efficient hot water system in the commercial food service industry, please refer to the companion design guide or the companion presentation. For more information than is contained in any of these resources, please feel free to reach out to Amin Dalaga or Michael Slater, who are both accessible at the email addresses listed on this slide. Thanks again.